Y20 interference of light waves. In this section, we consider the interference pattern generated by many light sources, especially two coherent light sources. Coherent means monochromatic. And no phase difference. We have two light sources, and it is generating circular wave on a plane, just like on water. Single wave, single light source. We have two light sources. We cannot distinguish where they are. However, we can find the amplitude is maximum in here, but in here, amplitude decays. If you, this distance d is the distance between the two light sources in units of the wavelengths, it becomes comparable to the wavelengths. We can clearly see the amplitude decays and magnified in here. If d is 2 lambda, 4 lambda, if you increase, the pattern becomes more dense, This pattern, interference pattern, becomes more dense. Okay, we are approaching the limit of diffraction. Okay, two radio waves are being generated from its origin. We have 1/2 of d vector minus 1/2 of d vector. Circular wave, two waves are generated at 2 points. In here, wavelengths lambda, these two wavelengths are the same. That means monochromatic. In addition, they are making two waves without phase difference. However, even though they are generating the same type of wave simultaneously, only in the middle they are always in phase. However, if you put a point P and this wave travels along this different path, and this distance and this distance are different. So rotate this one and you will find there is a path length difference. If the path length difference is an integral multiple of the wavelength, that should be constructive interference. In case this path length difference is half integral multiple of the wavelength, then destructive interference appears. By the way, if you add two sinusoidal waves traveling along a single direction, destructive interference must be complete, and constructive interference must be complete. That is a factor of 2, and that is a 0. However, because the amplitude dies out, attenuates as this circular wave travels, therefore, there you can see some fringes. However, those fringes are not perfectly double or perfectly zero. The, the cancellation is not perfect. Addition is not the same as double. Okay? The path length difference between the two from a single point to two sources at minus 1/2 of d and plus 1/2 of d and point of interest, where we measure the interference pattern. The length difference, point coordinates x comma y, subtraction, and if A is an integral multiple of lambda, it is constructive, and if it is a half integral multiple of lambda, then it should be destructive. And if you rearrange this equation, just leave this one on the left side and move this one to the right side and square this equation, you will find this square root disappears and this square root disappears. However, because the product, the 2 times a square root survives. And arranging this equation, move these guys to the left-hand side and square this equation once again. Finally, you end up with this kind of relation. This is, in fact, a parabola. The general form of parabola is like that. You divide both sides with this number, then you can find on the right side becomes 1, and x squared divided by 1/2 of a and y squared subtracted by y squared divided 1/2 of b squared is 1. In here, we have a special condition, distance d between the two sources squared should be sum of a squared and b squared. And in mathematically, this is a hyperbola. A hyperbola equation is something like that. And we call this A is a path length difference of this our original problem. And we have asymptote as x and y goes to infinities, plus minus infinities, then if it is very large, then this 1 can be ignored. So it is approximately 0 in comparison with x and y. And equals 0 becomes the equation for the two asymptotes. So they approach the two asymptotes. Okay. So A, B, so they are related to, we call this major, semi-major axis, or 1/2 of A is a semi-major axis, and A is a major axis, and B minor axis. And the eccentricity of a hyperbola is defined by d over A. That is always greater than 1. So let us investigate the interference pattern when the distance d between the two sources is the same as the wavelength. In this case, we have interference pattern at which it is magnified in here and in here, destructive, constructive, destructive. As the distance to d is 4 lambda, so wavelength becomes a very 4 lambda. Distance is much larger than the wavelength, then the interference pattern becomes a very dense. Okay. diffraction. So left figure shows a single point source generating radial wave of wavelength lambda, and this distance will be the wavelength lambda. We have a single wave. What about figure in the middle shows the resultant wave of n equals 10 coherent waves. Here we considered only 2 coherent waves. In here we have 10, 3, 4, 5, 6, 7, 8, 9, 10 coherent wave concentrate on a very short distance. If you list 100, you will find this kind of shape. Okay, the shape shows the Huygens principle. If you align coherent waves that are generating circular or radial waves, then the resultant wave of many sources of coherent waves will make a kind of plane wave. Features of diffraction. Light waves can reach in a wider area rather than a single point after passing through an aperture. I mean, if there is a hole, a plane wave travels in here, and when it passes through this small hole, actually it can be interpreted as a sum of many circular waves because they are blocked and only tiny sources generate circular wave that passes through this hole. So after passing through an aperture, this plane wave among this plane wave is the sum of many circular waves, and only tiny pieces of circular wave survives. Therefore, it is not traveling straight, but traveling radially. As a result, yesterday you have seen red moon, because the light travels from the sun is blocked by Earth, and the sun is bigger. However, it is very far away. Moon was in the middle, and we have experienced a lunar eclipse. However, this white light consists of many spectra. Among them, the red light has the longest wavelength that has stronger diffraction property. Therefore, the blue light scattered away, and this red light could reach there with this kind of form. Diffraction happens in here. If you draw a straight line, it cannot travel to the moon. However, because of the diffraction, and diffraction is magnified for the long wavelength case, so you have seen the red moon during the lunar eclipse. Okay, so for fixed wavelength, smaller aperture becomes smaller, then more diffractive. For a fixed aperture A, you have shorter wavelengths and longer wavelengths, and this longer wavelength lambda could be dominating the diffractive pattern. And these are all consistent with Huygens' principle that plane wave can be interpreted as the sum of many coherent radio waves. Young's experiment uses a single light source, and at the center, the distance from these two slits are the same. And single light source generate the radial wave, and when they reach the two apertures, then the two light sources generate the radial waves independently. And finally, you will find the interference pattern between the two light waves. And they are coherent because we have managed the original light source in here with the equal distance. So when they depart these two apertures, they were in phase. However, when they reach another point in the field point, because of the difference in the length, path length difference, will generate the fringes. That is called interference pattern. You will find distance d is 4 lambda, 2 lambda. You will find this diffraction pattern is magnified in this case rather than this. For example, we have d. You will find diffractive pattern. This one is more diffractive and less diffractive. You have many fringes in here. This fringe is very wide. And if you install two double slit in here and two coherent light being generated from this slit 1 and slit 2, and there is a screen very far away with a distance capital D. And this distance small d is the separation of the two apertures. If you put a point P in here, connect them, because it is very far away, we can draw a figure exaggeration. This point P can be the same P is in here because these two lines are parallel. So forget about this part because they are of equal distance, and this tiny delta L path length difference between the two paths should be, this part is magnified in here, and if you measure the angle theta in here, that is identical to theta in here. Therefore, the distance small d multiplied by sine theta should be the path length difference between the two light waves. If this path length difference is an integral multiple of the wavelength lambda, then you will find maximum bright points, so bright fringes. If it is a half integral multiple of wavelengths, then it becomes minimum. This one can be understood by introducing the idea of Maxwell's theory of electromagnetism. Once we consider the electric field, the magnetic field is dependent on the electric field in the sense that they are in phase, and you have a wave vector electric field and magnetic field, this is completely dependent. They are in phase. So let me just concentrate on electric field only. The, the two light waves coming from the slit 1 and slit 2 to point P on a screen can have a phase difference due to the path length difference, that is the d sine theta. So d sine theta is scaled by the wavelength, and if it is a multiple of 2 pi, then it becomes the bright point. And if we add these two waves, we know how to add up two sinusoidal function. Same thing, 2 multiplied by the original amplitude multiplied by cosine of half of angle, half of phase difference. Using this, we substitute this electric field to the intensity. Intensity of the electromagnetic wave is sum of electric field and magnetic field, and we know the energy density should be the same, and in terms of RMS value, we can express it like that. Therefore, the sum of the net electric field can be used to find this intensity. And this intensity coming from this original electric field that depends on the sine 1/2 of phi, and then its amplitude, the brightness should be proportional to the amplitude squared. So we have cosine squared 1/2 of delta. So this relation is the key formula to determine where the bright and dark points are placed. And this one is drawn in here, depending on the phase difference originating from the path length difference.